Munson 359 has this odd-looking configuration. There's a siphon here, so this pipe is coming from inside the tank. Water is coming through the pipe, around the corner, and spraying up against the wall here. So the jet comes out of the pipe, hits the wall, sprays off in both directions. And the question is asking us, at point A here, which is going to be a stagnation point, what's the pressure? So that's a stagnation pressure. And what's the flow rate through the tube? And it also says we can ignore friction, which is not a good assumption, but it's the best assumption that we can make at this point in the course. So to find the flow rate, we'll need to find the velocity coming out of the pipe here. And so we'll write Bernoulli's equation between two locations. The obvious one is put 1 up here on the surface, because that's where we know something. We know it's atmospheric pressure. We know the fluid's not moving. We'll draw a streamline that comes down through here, up through the pipe, all the way around, and back out over here. And we'll call this location 2. So we can write Bernoulli from 1 to 2. Z1 plus P1 over rho g plus V1 squared over 2g equal to Z2 plus P2 over rho g plus V2 squared over 2g. Always write out the whole equation and then carefully cross out the things that turn out not to matter, and things will work out okay. If you try to just jump to the reduced equation, you're likely to get into difficulty. So let's look at the pressures. The pressure at location 1 is atmospheric, and the pressure at location 2, right where it discharges from the pipe, is atmospheric. Because in the air here, there's very little pressure difference between those two locations. So P1 and P2 are both atmospheric. Z1 and Z2 are different from each other. V1 is equal to 0. As long as this tank is fairly large compared to the pipe, which it sure looks like it is, V1 is for all intents and purposes 0. So rearranging, we can wind up with V2 equal to 2 times G times Z1 minus Z2. And that would be V2 squared. So take the square root of that. And that'll be 2 times 9.81 times Z1 minus Z2 is 3 meters, all square root. So V2 is equal to 2 times 9.81 times 3 is about 59. Take the square root of that. We get 7.67 meters per second. And what is the flow rate? Well, Q going through location 2 will be V2 A2, Q equal VA. So that'll be 7.67 times pi times d, it's 0.4 meters in diameter, squared over 4. So taking our 7.67 times pi times 0.4 squared divided by 4, and I get 0.964. 0.964 cubic meters per second. That seems like an awful lot. That's a ton of water every second, just about. But hang on. This pipe is 0.4 meters in diameter. It's enormous. 0.4 of a meter is more than your hand span. 0.4 of a meter is this big. Okay, I can believe that there's almost a cubic meter per second coming out of that pipe. So always test your answers with questions like that to see if the answer that you get makes sense. Now, what's the pressure when it hits the wall? Well, it comes out of here and it's going 7.67 meters per second, and A is going to be a stagnation point. So we can write Bernoulli between location 2 and location 3 this time. Z2 plus P2 over rho G plus V2 squared over 2G equal to Z3 plus P3 over rho G plus V3 squared over 2G. We can always write Bernoulli along a streamline between any 2 points. We could write it directly between 1 and 3, in fact. So let's see if we get the same answer both ways. Here we've written it between 2 and 3. And if we ignore the elevation change, this jet might drop down a little bit, but let's ignore that for the moment. And at the same time that we're ignoring that, we'll say it also doesn't accelerate due to gravity. So it'll work out. So we'll say that Z2 and Z3 are equal. We'll say that P2 is atmospheric. And we'll say that V3 is 0 because it's a stagnation point. And we wind up with P3 equal to rho V2 squared over 2. That'll be 998 for our water times V2 squared is 7.67 squared, all divided by 2 is 7.67 squared times 998 divided by 2 is 29356 pascals, or 29.4 kilopascals. Now let's see if we get the same answer if we went straight from point 1 to point 3. Z1 plus P1 over rho G plus V1 squared over 2G equal to Z3 plus P3 over rho G plus V3 squared over 2G. Now P1 is atmospheric, P3 is higher than atmospheric, it's that stagnation pressure. V1 is equal to 0, V3 is equal to 0, and we should wind up with the stagnation pressure, P3, being rho G times the height difference. P3 equal to rho times G times Z1 minus Z3. That'll be 998 times 9.81 times height difference of 3 meters. 998 times 9.81 times 3 is 29371. Pascals. Now that's not quite exactly the same answer as there, but I think it's certainly the same answer to within the round-off error. Our differences are lying out here in the fourth significant figure. So yeah, we can apply Bernoulli's equation along any streamline, And we can skip point 2 in the middle if we want to, but we didn't skip it because we wanted to find out what the velocity was and what the flow was.